Hello and welcome to our presentation on the Brewster's angle and the viability of a smartphone as a spectrometer. This is for class physics 3330 modern optics, and this is narrated by Robert Bull in cooperation with Daniel Desena. Over the course of this presentation, the topics that will be covered are the introduction of our experiment, the objective of our experiment, the experiment design, the theory, data analysis, and conclusions drawn. In designing this experiment, our goals were to measure the Brewster's angle and refractive index of different solutions with varying percentages of glucose syrup, and to test the viability of using a smartphone as a spectrometer. The topics covered over the course of this lab are polarization, or the restriction of the electric field of an electromagnetic wave to a single pattern or plane. This manifests in the case of linearly polarized light, typically denoted as S or P for the electric field perpendicular to the incident plane and parallel to the incident plane respectively, and circularly polarized light or elliptically polarized light. For this lab, we will specifically be dealing with p-polarized light given our plane of incidence, and also the Brewster's angle as discussed later on. The reflectance of light is the percentage of light reflected off of a surface respective to the incident light beam. The Brewster's angle is a particular angle with regards to the polarization or lack thereof, in the case of natural light, of light. And for the Brewster's angle, it is a specific case in which, depending on the incident plane, polarized light will not reflect, and natural light will only reflect as polarized. This will be discussed further on in the presentation. And lastly, just smartphones. Smartphones can be considered almost as the peak of optical instruments in modern times, and as such, it was our goal to demonstrate using a smartphone as a spectrometer or an optical instrument and the viability of a smartphone in difficult situations. In designing this experiment, we had to abide by three major constraints. Our first constraint was that the petri dish contained a liquid which could spill. In addition to this, we could not have the light beam enter and transmit through a container of sorts because that would alter the reflected beam. Our second constraint was the size and weight of the phone and parts necessary. This was a constraint because it meant that we would not be able to 3D print an apparatus without considerable difficulty. Instead, we used wood as our main constructive material, which allowed us to work around this. Lastly, our third constraint was a $30 budget, which guaranteed we could not outsource for other resources and had to be creative in our experiment design. As you see in front of you, we decided on using a T-shaped block and two supportive arms. On arm 1, we have mirror M2, which the incident beam is redirected into using mirror M1. And on arm 2, we have the smartphone, which was attached to a wooden block using a clamp. The beam was reflected off of the petri dish containing the solution and into the camera of the smartphone, which we then took a picture of the beam. Our project relies on Fresnel's equation for p-polarization. This is an equation relating the angles of incidence and transmission and the indices of refraction. We square this in order to obtain a value called the reflectance, as mentioned earlier in this presentation. Rewriting the Fresnel equation using Snell's law, as well as trig identities, we obtain the reflectance, denoted as capital R. When the intensity is 0 for reflected p-polarized light, we can obtain the equation for the Brewster's angle, seen in this slide, as well as the refractive index of the solution. Fresnel's equations guarantee that a Brewster's angle will not be encountered for light that is polarized other than perpendicular to the plane of incidence. Our data is split into two sections: obtaining the Brewster's angle / calculating the refractive index of different solutions, and measuring the reflectance of light at different angles for different solutions. For data section 1, we started with a pure water solution and found the Brewster angle to be equal to 51.71 degrees. In comparison to the actual Brewster angle of water, given as about 53 degrees, this yields a percent error of approximately 3%. From there, we increased the glucose syrup concentration in increments of 5% and found the Brewster angle to be as you see in front of you. In addition to this, we calculated the index of refraction from the equation mentioned in the theory slide to be as seen in this column. Lastly, we compared the error between data section 1 and data section 2, just for sake of mentioning the consistency in our methods, though this does not bear meaning until we cover the data section 2, as seen later on in this presentation. When graphed, you can observe an almost, if not linear, relationship between the Brewster angle and glucose concentration. In comparison to similar research, this is consistent with other people's results. For data section 2, we took pictures of the reflected beam directed into the iPhone XR camera and captured pictures at 2-degree increments, starting at an incident angle of 47 degrees and ending at an incident angle of 75 degrees. In addition, we used Python to sum the pixel intensity per column. This summation was done using arbitrary units, however these units were constant, resulting in a consistent graph shape. This data, in blue, was fitted using the reflectance equation mentioned earlier in this presentation, resulting for water in a p-value of 0.69 and a chi-squared value of 6.5. For glucose, this process resulted in a p-value of 0.5 and a chi-squared value of 8.4. This slide shows some of the captured pictures for water in addition to the Python mapping of the pixel intensity. For the points on the previous slide, the entire graph was summed and calculated into a single point. In total, there were 10 pictures and graphs. However, we're only showing 3 by 3 for sakes of convenience. This process was again repeated for the 45% glucose concentration solution. We did not continue to do this process for the other increments of glucose concentration because this section of the lab was merely to demonstrate the viability of the iPhone as a spectrometer, and further continuing on with this data would be redundant. In conclusion, there were two major sources of error encountered during this lab. First, there was no way to guarantee that no light interference would seep into our camera frame as we were collecting data. In addition to this, the nature of a smartphone camera is such that if there is any light in the background, it will try to pick that light up. To avoid this, we attempted to focus the camera on the background darkness, which was consistent across our pictures. However, we still encountered error. In addition to this, the sensitivity of this apparatus was very hard to work with. It was almost impossible to always center the beam perfectly into the middle of the iPhone camera, and as such, this caused some variability in our data as seen in our graphs. From our lab, we can conclude from our low chi-squared values that our methods were fairly precise. However, our also somewhat low p-values meant that our methods were not too accurate and limited results can be drawn from our graphs. it is accurate to say that an iPhone XR can serve as a viable spectrometer in this setting. Thank you for listening. This lab was again constructed by Robert Bull and Daniel Desena. Good day.